So in this video, we're going to talk about how to graph a rational function. So we have what are called holes of rational functions. Remember that a hole will be plotted as an open circle on the graph of a rational function because that's a point where the function does not exist. We also have horizontal asymptotes on rational functions. Those will show you the end behavior of the function. The horizontal asymptote will show you the value that the function approaches as x approaches negative and positive infinity. So the zero of the rational function is going to be the x-coordinate of the x-intercept. Remember, the x-intercept is the point where the graph crosses or touches the x-axis. So here's how you graph rational functions. You're going to start off by factoring the numerator and denominator if possible. Then you're going to identify any holes, then determine the zeros of the function, determine the asymptotes of the function, determine the domain and range, then create a table of values choosing a few x values on either side of any vertical asymptotes. Remember, when you do the table of values, you want to use the simplified version of the function that you've created by canceling any common factors. Then you're going to sketch the graph. Draw asymptotes as dashed lines, plot points from the table, and plot holes as open circles. Connect the points extending the branches of the function toward the asymptotes. So let's determine where f of x equals negative 2 times x plus 5 times x minus 4 over x minus 1 times x plus 3 times x plus 5 crosses or touches the x-axis. So you always want to start off by factoring the numerator and denominator. Well, in this case, the problem's already factored for you. So what we can do is we can go ahead and identify any holes by looking for any common factors. Notice that this x plus 5 and x plus 5 are a common factor that we have. So we're going to go ahead and we're going to cancel out that common factor, and we're also going to use it to determine a hole. So when we cancel it, we have the simplified function, f of x equals negative 2x times x minus 4 over x minus 1 times x plus 3. So what we're going to do is we are going to now figure out the hole. We have x plus 5 equals 0. So if we subtract 5 from both sides, that tells us that x equals negative 5. So that's going to be that x-coordinate of the hole. So what we're going to do is we're going to plug in that negative 5 into this simplified function to figure out the y-coordinate. So we have f of negative 5 equals negative 2 times negative 5 times negative 5 minus 4 over negative 5 minus 1 times negative 5 plus 3. So when we do that, we get 10 times negative 9 over negative 6 times negative 2. So that gives us negative 90 over 12, and negative 90 over 12 will just become, when we reduce it, 15 over 2. So we have negative 15 over 2, which equals negative 7.5. So our hole will occur at negative 5, negative 7.5. Now let's go ahead and figure out any zeros of the function. Remember, zeros will occur where the function equals 0. So what we're going to do is we're going to take this numerator and set it equal to 0. So we have negative 2x times x minus 4 equals 0. So that tells us that negative 2x equals 0 and x minus 4 equals 0. So when we do this, we add 4 to both sides, and so that tells us that x equals 4. And then we divide both sides by negative 2, and we get x equals 0. So the x-intercepts are going to occur at 0, 0, and at 4, 0. So now let's figure out the asymptotes of the function. So remember, the vertical asymptotes are going to occur anywhere where the denominator equals 0, right? So I'm going to take that simplified function and I'm going to set the denominator equal to 0. So that denominator is x minus 1 times x plus 3. So I set that equal to 0. And then I'm going to solve for x. So that gives me x minus 1 equals 0 and x plus 3 equals 0. So I'm going to add 1 to both sides, and that gives me x equals 1, which is one vertical asymptote. And then I subtract 3 from both sides, which gives me x equals negative 3. That's another vertical asymptote. So for the horizontal asymptotes, we're going to think about the degree of the function, right? So the degree of the numerator, we have 1, 2, 3x, right? So that has degree 3. And the denominator, we have 1, 2, 3x. That also has degree 3. When it has the same degree, remember we do the ratio of the leading coefficients. So the ratio of the leading coefficients, so for the horizontal asymptote, we're going to say y equals, and then we're going to do the ratio of the leading coefficient of the numerator, which is 2. In the denominator, there's no leading coefficient, so that's going to be 1. So we do negative 2 over 1, which equals negative 2. So y equals -2 is the horizontal asymptote. So now what we're going to do is we're going to go here and we're going to graph this function. So you may have noticed that my table is already filled in. So what I did is I went and I plugged this into Desmos. Okay, so I entered this all in Desmos, and then what I did is I clicked on each of these x values, and then it gave me these coordinates that I have listed here. Okay, so you can do this in Desmos, or you can do it in your TI calculator. You're just going to click second, and then you're going to click table. Okay, and it'll give you the table of values that you can use to fill in this table. So remember, you always want to start off by sketching in your asymptotes. So remember, we have vertical asymptotes at x equals 1 and x equals -3. So those are sketched in here with those dotted lines. Let's also go ahead and sketch in our horizontal asymptote, which is at y equals -2. Because remember, that's going to tell us the end behavior of the function, right? What does the function do as x heads to positive and negative infinity? So now let's go ahead and plot these points. So we have -6, -5.7, -4, -12.8, and then -3, it doesn't exist. So this is going to be one piece of our function, right? It's going to go like this. And then that horizontal asymptote tells us the end behavior. So the graph is going to go like that. And then we have the points -2.8, -1, 2.5, 0, 0. And then at 1, it doesn't exist. So we're going to have this second piece that kind of goes like this. Because remember, it's just going to get really, really close to that vertical asymptote, but never really cross it. And then we have this final piece. So we have 2 and then 1.6, 3.5, and then 4, 0. So it's going to go like this, right? Not crossing the vertical asymptote, but then the horizontal asymptote is going to tell us what happens as x approaches infinity. So it's going to go like that, okay? So I'm going to outline these in a different color just so you can see it a little bit better. So we have one piece here in the middle, okay? We have another piece on this end. And we have another piece over here, okay? So our function is actually in 3 pieces. Okay, so now let's figure out what's going on when we have the function f of x equals 2x squared plus 10x over x squared plus 6x plus 5. Remember, the first step is always to factor the numerator and denominator whenever possible. So let's factor 2x squared plus 10x. Notice that these have a GCF. The GCF is going to be 2 and also x. So we're going to factor out 2x, and then we have 2x squared over 2x plus 10x over 2x. And so we have 2x times 2 and 2 cancel, and then we have x squared over x, which is x, plus 10 over 2 is 5, and then x and x cancel. Now let's factor the denominator. So we have x squared plus 6x plus 5. So we need 2 factors of 5 that are going to add up to 6. Since 5 is positive and 6 is positive, we're going to have 2 positive factors. So we are going to have 1 and 5, and 1 and 5 does add up to 6. So we have x plus 1 times x plus 5. So when we factor this, we have f of x equals 2x times x plus 5 over x plus 1 times x plus 5. So now what we're going to do is identify any holes. So notice we have this common factor of x plus 5 and x plus 5. Okay, so the hole is going to occur at x plus 5. So we have x plus 5 equals 0, and we're going to subtract 5 from both sides. So when we do that, we have x equals -5. Let's go ahead and write the simplified form of this function by canceling out that common factor. So we have 2x over x plus 1. If we plug in -5, we have f of -5, which is 2 times -5 over -5 plus 1. So that's -10 over -4. So that is going to be 2.5, right? Because that's going to be 5 over 2. And so that is the y coordinate of the hole. So we have a hole at -5, 2.5. So now let's determine any zeros of the function. Remember, you can find zeros by taking the numerator and setting it equal to 0. So the numerator is 2x equals 0. And so when we divide both sides by 2, that gives us x equals 0. So we will have a 0, right, or an x-intercept at 0, 0. Okay, so just another thing to watch out on our function. Now let's go ahead and determine the asymptotes. So we have vertical asymptotes and we have horizontal asymptotes, right? So the vertical asymptote, we're going to take this denominator and set it equal to 0. So we have x plus 1 equals 0. Subtract 1 from both sides, so we have x equals -1. That's our vertical asymptote. The horizontal asymptote, we look at the degree of the numerator and denominator. Well, notice that both of these have degree 2. Okay, so we're going to take the ratio of the leading coefficients, which are 2 and 1. So we have y equals 2 over 1, which equals 2. So the horizontal asymptote is going to be at y equals 2. So now let's go to our grid. Okay, so here we have our vertical asymptote, which is at x equals -1. Let's go ahead and draw in our horizontal asymptote at y equals 2. So that is going to be here. And let's also plot the 0 that we have, right? So remember, we have a 0 at 0, 0, and we have a hole at -5, 2.5. So let's go to -5, 2.5, and put our hole there. And our 0, 0 is our x-intercept. Okay, so now let's plot these points. So once again, I got these points by entering the function in Desmos, or you can do it in your TI calculator, and I filled in my table of values. So we have -4, 2.67, -3, 3, -2, 4, and then we just connect those points and use the asymptotes to kind of figure out the end behavior, right? So it's going to go like this. And then we have this piece over here. So we have 0, 0, our x-intercept, right? So it's going to get really, really close to that vertical asymptote, but not cross. And then also that y, our horizontal asymptote is going to tell us what the function does as x goes to positive infinity. So it's going to have two pieces that look like this. Okay, so using those points and using the information from the asymptotes, you can kind of sketch in the graph of your rational function. Remember, you can always double check by graphing these in Desmos and comparing it with the graph in Desmos. So now you can go ahead and pause the video and try this example on your own. So in this example, we factored the denominator. So since there's no common factor, we have no holes. We also have no zeros in our function because if you set the numerator equal to 0, you just get -3 equals 0, which isn't really anything. So if you look at the factors of the denominator and set them equal to 0, we have x equals -3 and x equals 3 as our vertical asymptotes. Notice that the numerator, it has a degree of 0, right? Because if there's no x there, that's x to the 0. So the degree of numerator is less than the degree of denominator, so the horizontal asymptote is at y equals 0. So if we go ahead and do this, we know the domain is going to go from -∞ to -3, and then from -3 to 3, and then from 3 to infinity. The range is going to go from -∞ to 0 and 0 to infinity. So now we're going to have three pieces of this graph. We went ahead and plotted these points that we got from Desmos. Notice that we have our vertical asymptotes here, right? The vertical asymptotes at x equals -3 and x equals +3. Our horizontal asymptote is actually the x-axis, right? Because that is y equals 0. So you can see that shows you the end behavior of the function, right? Where it's going as x heads to positive and negative infinity. So using all this information, we can kind of piece together the graph of the rational function. So remember, to graph rational functions, you're going to factor the numerator and denominator if possible, identify any holes, determine the zeros of the function, determine the asymptotes of the function, then determine the domain and range of the function. Then you're going to create a table of values, choosing a few x values on either side of any vertical asymptotes. Remember to use the simplified function to do this. Then you're going to sketch the graph and draw asymptotes as dashed lines, plot points from the table, and plot holes as open circles. Connect the points extending the branches of the function toward the asymptotes.